When we look at the Himalayas, we see the youngest, highest, and most formidable wall of rock on the planet. They seem permanent and immovable, but the water flowing through these peaks hides a geographical paradox. The river is actually older than the rock itself. Millions of years ago, before the Indian and Eurasian tectonic plates crashed together to build these mountains, a massive water network was already flowing. Geologists call this process antecedent drainage. It means the river predates the topography. As the tectonic collision forced the Earth upward millimeter by millimeter, the rushing water acted like a buzzsaw, slicing straight down into the rising rock at the exact same rate. That relentless downcutting physics is the exact reason we find a turquoise river trapped at the bottom of such incredibly deep, steep-walled canyons today. The water didn't find a path through the mountains, it carved it. The Ganga functions as a predistorted geological engine, a force that continues to dictate the physical reality of the entire Indian subcontinent. The engine starts high in the mountains. If we trace the water back to its source at this jagged glacier in Uttarakhand, it isn't even called the Ganga. Here, it is a single, violently fast stream known as the Bhagirathi. But the Bhagirathi needs raw power, and it gets that from its lead architect, the Alaknanda River. The Alaknanda is an entirely separate, massive stream that gathers water from highly significant cultural valleys, like the one surrounding the Badrinath temple. These rivers combine through a geographical funneling process known as Panch Prayag. These are 5 distinct deep mountain confluences where the geography forces separate river systems to collide. At each confluence, rivers like the turbulent Pindar and the deep Mandakini slam into the Alaknanda. These collisions concentrate the water mass and accelerate the river's kinetic energy, giving it the pressure required to erode through layers of solid rock. Finally, at a specific gorge called Dev Prayag, the heavily armed Alaknanda merges with the original Bhagirathi. Only here, after merging their separate colored waters, does the stream officially take the name Ganga. This entire mountain phase is a high-energy gathering mechanism. It arms the water with pulverized rock and immense pressure, preparing it for the next phase of the journey. The physics of the river shifts the moment it leaves the mountains and arrives at Hardwar. Here, the water hits flat, open terrain for the first time. This top-down map shows what happens next. Because the water hits flat ground, it loses the kinetic energy needed to carry heavy mountain rock. The river undergoes deposition, dropping its debris over thousands of miles to build the vast alluvial plains that support nearly 500 million people. As it moves across these plains, it pulls in more water. The Gomti tributary proves that a river in this system doesn't even need a glacier. It originates entirely from a flatland lake, fueled by groundwater and rain before joining the main channel. The volume of water moving through the plains sustains massive regional economies. The Gandak tributary directly feeds the Triveni Canal, which provides the irrigation necessary for the region's agricultural output. But the same deposition process is also destructive. From the left bank in Nepal flows the Kosi River, carrying an exceptionally massive load of sand and mountain sediment. The Kosi drops its heavy sediment so rapidly that the debris physically clogs the riverbed. The water becomes choked, snats out of its established boundaries, and carves new paths across the land. This unpredictable flooding is why the Kosi is known as the Sorrow of Bihar. These plains are entirely constructed from the exhausted debris of the river. The same geological machine that created the land also provides the fertile soil and water required for its biological survival. While the northern rivers bring mountain sediment, a huge secondary network feeds the Ganga from the south. The Yamuna, the deep ravines of the Chambal, and the northward flowing Son River all pump water up from the peninsular plateaus to join the main system. By the time this combined system reaches the Farakka Barrage in West Bengal, it is carrying an almost incalculable amount of mud and silt. Eventually, the sheer weight of that sediment breaks the river apart. As the flow slows, the weight of the accumulated sediment becomes so great that the main channel physically blocks itself. The water is forced to splinter into distributaries like the Hooghly and the Padma, seeking any possible path to the ocean. These distributaries eventually merge with the Brahmaputra. Together, they dump their final microscopic traces of mountain dust into the Bay of Bengal, forming the Sundarbans, the largest mangrove delta on Earth. But the scale of this ancient natural engineering hides a modern vulnerability. Take the Damodar tributary, which flows from the southern plateaus. Today, scientists classify it as a biological desert. Decades of industrial runoff from coal mines have completely stripped the Damodar of its dissolved oxygen. Because the river's chemistry has been altered, the life it was meant to sustain can no longer survive in it. The Ganga is an ancient engine, powerful enough to carve mountains and build land masses. But while its geological strength is absolute, the biological survival of the system is not, proving that the civilization built by this machine is also capable of breaking it.